Okay, then let's start with part 2 of the all chapters revision. I was still in D and F block, so let's continue from there itself. I was explaining oxidation of nitrile ion by oxidation reactions of potassium permanganate. The next reaction is oxidation of nitrile ion by potassium permanganate. Nitrile ion. This is not nitrite, not nitrile, it is nitrite. Nitrite ion is oxidized to nitrate ion, where nitrite is NO2 minus, nitrate is NO3 minus. The reaction is here, the reaction is 2MnO4 minus plus 5NO2 minus plus 6H plus gives 2Mn2 plus plus 5NO3 minus plus 3H2O. This is the reaction. MnO4 minus plus nitrite plus 6H plus. So individually we can write it as NO2 minus becoming NO3 minus. I think there might be O2 here. Somewhere it should get the O2. But generally the equation should be something like this. 2 electron okay, then into 5, this will become 5NO2, 5NO3 and 10 electron, which matches this, and MnO4 minus into 2, there should be 8H plus here, but it became 6H plus, possibly because here there might be some H plus. Okay, let's just, it might be better to just remember this reaction. Now coming to the next reaction, oxidation of sulfurous acid or sulfite ion by KMnO4. The reaction is 2MnO4 minus plus 5SO3 2 minus plus 6H plus gives 2Mn2 plus plus 5SO4 2 minus plus 3H2O. Here it is oxidation because the oxidation state of SO4 SO3 2 minus, here it is X minus 6 plus minus 2, so it is plus 4, here it is plus 6, it is getting oxidized. In this reaction here, the oxidation state of nitrogen is plus 3, it is getting oxidized to plus 5, it is gaining and losing 2 electrons. Now, these are the acidic medium reactions. In acidic medium, acidified potassium manganate. In case of neutral medium, we know that potassium manganate is a strong oxidizing agent in all neutral, basic, and acidic mediums, but the reaction is different. There is a reaction, uh, KMnO4 reaction with iodide in neutral medium. The reaction is something like this. It oxidizes iodide into iodate. Iodide I minus 2 IO3 minus iodate. Here it is minus 1 oxidation state. Here it is plus 5 oxidation state. The equation is I minus plus KMnO4 or 2MnO4 to MnO4 minus plus H2O gives 2MnO2 plus 2OH minus plus IO3 minus. Here in this case, plus 7 to plus 4. In the first case, in acidic medium, manganese was got oxidized from, I mean, no, it got reduced from plus 7 to plus 2. Here in neutral medium, it got reduced from plus 7 to plus 4 only. That's the reaction. Then let's go to the next reaction. KMnO4 oxidizes manganese salt in neutral or alkaline medium. It converts manganese salt to MnO2 in presence of zinc sulfate. I'll write it here. Or zinc oxide. In neutral medium, the reaction is 2MnO4 minus plus 3Mn3 plus 2, 2 plus the manganese salt is Mn2 plus salt plus 2H2O gives 5MnO2 plus 4H plus. That is a reaction MnO4. We basically saw three reaction: one with nitrite, one with sulfite, sulfurous acid or sulfite ion, then iodine, then that's all. Permanganate titrations in presence of hydrochloric acid are unsatisfactory. This is a point. Permanganate titrations in presence of HCl are unsatisfactory. As for the reason, it is because hydrochloric acid is oxidized to chlorine by permanganate ions. Because hydrochloric acid converted to Cl2 by KMnO4, which is not needed. That's with so hence primary standard, since KMnO4 can't be used everywhere, primary standard of quantitative analysis or volumetric analysis K2Cr2O7 is used or preferred. Potassium dichromate is preferred. It is the primary standard. Now coming to that's the end of D block. Coming to inner transition elements or F block. F block inner transition elements. What are F block elements? Elements in which added electron enters into n minus 2 f orbital or anti-penultimate shell are called F block elements. There are two series: 4F lanthanides, 5F actinoids. Their general electronic configuration is noble gas n minus 2 f1 to 14 minus n minus 1 d 1 to 10, I mean 0 to 1, ns 2. This is the general configuration. They are called inner transition elements. Why are they called inner transition elements? Because the added electrons enter anti-penultimate n minus 2f subshells, hence called inner transition elements. These are the main characteristics. As for names, I mean the lanthanides start from cerium 58 to lutetium 71. Actinide starts from thorium to lawrencium. As for their atomic numbers, 90 thorium and 103 lawrencium. 90 thorium and 103 lawrencium. This is a general summary about the inner transition elements or F block elements. Okay, coming to lanthanides specifically. Lanthanides, they are called rare earths from cerium to lutetium. General electronic configuration is xenon 4f1 to 14, 5d0 to 1, 6s2. This is the general electronic configuration. What is lanthanide contraction? There is a specific topic that is very important here. Lanthanoid contraction. The gradual decrease in atomic and ionic radii from lanthanum to lutetium is called as lanthanide contraction. Gradual decrease in atomic and ionic radius from lanthanum to lutetium is called lanthanoid contraction. The causes of lanthanide contraction, we have heard about screening effect. Screening effect is the effect which inner electrons contribute by repulsion and increase the size of the atom. We know that we need to know that the f orbital is very bad at shielding. The f orbitals are very bad at shielding. Like the order goes something like this: s orbitals are the best at shielding, p orbitals second best, then d orbitals are weak at shielding. The weakest is f orbitals. So hence, as the screening effect decreases, as we and normally the size decreases from left to right. This continues here because the screening effect becomes negligible or very less in case of f orbitals. They are very bad at shielding due to their positions, which are like quadruple dumbbells, and because of that, the effective nuclear charge on the outer electrons increases, and as we go from lanthanum to lutetium, the nuclear charge keeps on increasing, and the f orbital shielding remains the same. So because of the nuclear charge, the size decreases. That is lanthanide contraction caused due to the imperfect shielding of one electron by the other in the same set of orbitals. It is due to the effect of 4f electrons. Shielding of 4f electrons is less than 5d electrons with increase in nuclear charge along the series. Due to imperfect shielding of f orbital electrons. Any consequences of lanthanide contraction? Any problems we face due to lanthanide contraction or any benefits? Let's see. Due to lanthanide contraction, atomic radii of zirconium, it is 160 picometer, and hafnium is 159 picometer. It is almost same. So they occur together in nature. They occur together in nature and are very hard to separate. Like we cannot easily separate them. It's a headache to separate them. Covalent character of cations increases. Covalent character of cationic, first consequence due to lanthanide contraction, the atomic radii of zirconium and hafnium is almost the same, so they occur together, hence it is difficult to separate them. And second consequence, covalent character of cations will increase. Sure. Electronegativity increase the closer the smaller the atomic size, higher the nuclear attraction, so more the electronegativity. Basicity decreases from lanthanum to lutetium. This is the same, these both points are kind of similar. Covalent character of cation increases, meaning acidic nature of the cation increases. If acidic character of the nature of the cation increases means basicity decreases, ionic character decreases. SRP value, standard reduction potential value, increases, meaning they prefer more to be reduced. Then that's about lanthanide contraction. Now coming to one of the most important points of lanthanides, the common oxidation state of lanthanides. Common oxidation state, number of lanthanoids is +3. There are exceptions here. If we talk about exceptions, europium and ytterbium show +2 oxidation state. Because europium shows +2 to attain 4f7 configuration, ytterbium shows +2 to attain 4f14 configuration. This is half filled stability, this is fully filled stability. We saw chromium and copper examples, it is exactly similar. There chromium, here europium attains 4f7, ytterbium attains 4f14. There is one more exception, cerium, just after lanthanum. Cerium shows +4 oxidation state. It uh, because to attain here also electron stability, to attain noble gas configuration, xenon configuration, noble gas configuration, that is xenon 4f0 5d0 or 5d1. I think it's 4f0, that's all. Yeah, 4f0. A member of lanthanide series that is well known to exhibit +4 oxidation state is cerium. Cerium, europium, and ytterbium are exceptions which don't always have +3 oxidation state. Cerium shows +4 oxidation state to attain noble gas configuration. Europium shows +2 oxidation to attain half-filled stability. Ytterbium shows +2 oxidation to attain fully filled stability. The general characteristics of lanthanides. They are silvery white metals, and tarnish rapidly in air. Hardness increases with increasing atomic number. Meaning from lanthanum to lutetium, hardness will keep on increasing. Good conductors, good electric and thermal conductors. all lanthanide ions except lanthanum plus 3 and lutetium plus 3 are colored they are not colored because they have no unpaired electrons. Both in solid state and in aqueous state, due to presence of electron in f orbital. Lanthanide ions accept lanthanide ions except F0 configuration having we have lanthanum 3 plus and cerium 4 plus, these two, and fully filled configuration F14 type ytterbium 2 plus and lutetium 3 plus, except these are diamagnetic, remaining all paramagnetic. Then that's about the physical general characteristics. Coming to chemical properties of lanthanides, we just need to remember they have a plus 3 common oxidation state. So with that we can write the chemical equations easily. Chemical properties of lanthanoids. One, they burn with oxygen to form Ln2O3, lanthanum oxide, 4 Ln plus 3O2 gives 2Ln2O3. It is similar to ferric oxide, where ferric ion in ferric state has plus 3 oxidation number. Similarly, lanthanides have plus 3 oxidation state. So similarly, they will form a product similar to iron, not similar in physical or chemical, just chemical formula. Lanthanides combine with hydrogen when they are gently heated, forming hydrides. That is LnH3 formula, hydride, lanthan, lanthanoid hydrides. It's not lanthanum, it is lanthanoid hydride. Then 3, lanthanides form carbides when heated with carbon at 2773 Kelvin, very high temperature. Example, 3 lanthanum plus carbon gives lanthanum 3 carbide. 2 lanthanum plus carbon gives lanthanum tricarbide. Lanthanum plus 2 carbon gives lanthanum dicarbide. 4. They liberate hydrogen from dilute acids. 5. They burn in halogens to form halides. 2 Ln plus 3x2 gives ln x3. 6. They react with water to form hydroxides with liberation of hydrogen. 2 lanthanum plus 6H2O gives then form nitrides when heated with nitrogen. 2 Ln plus N2 gives 2 Ln. They react with sulfur when they are heated to form corresponding sulfides. 2 Ln plus 3 sulfur gives Ln2S3. These are the chemical properties of lanthanides. Let's just see them again. They burn with oxygen to give lanthanum oxide. They combine with hydrogen to give lanthanum hydrides. They combine with carbon to form carbides. Then they are heated with 2773 Kelvin temperature. Lanthanum plus carbon. These are the three ways. Then they liberate hydrogen from dilute acid, meaning they are basic in nature. They burn in halogens to form lanthanoid halides. They react with water to form hydroxides and liberation of hydrogen, form nitrides when heated with nitrogen, form sulfides when reacted with sulfur. Now, one of the most important metal or alloy or combination from lanthanum is mixed metal. Mixed metal composition and use. Composition is lanthanoid 95% plus iron 5% plus traces of sulfur, carbon, calcium, and aluminium. Mixed metal is used in Mg magnesium based alloy to produce bullets. Shell and lighter flint. That's about mixed metal. Basically used in bullet making. It is composition is 95% lanthanoid, 5% iron, and traces of sulfur, carbon, calcium, and aluminium. Now coming to actinoids. From thorium 90 to lawrencium 100 and no, 103 are actinoids. 5F series, added electron enter 5F shell. General electronic configuration, radium, radon 5F1 to 14, 6D0 to 1, 7S2. This is the general configuration of actinoids. Now a topic we saw before, a similar topic, actinoid contraction. Same thing, gradual decrease in size along actinoid series of atoms is called actinoid contraction. Cause is again due to poor shielding of 5F electrons, 5F orbitals. Common oxidation state of actinoids also is plus 3, but not, there are many exceptions. Like it is not so strict as lanthanides. There are many exceptions. Like we had only 4 to 5 exceptions, like ytterbium, europium, and cerium in lanthanoids, but in this case we will have many more exceptions. It is not so strictly followed. They show greater number of oxidation state. Greater number of oxidation states because due to comparable energies between 5F60 and 7S levels. Because of that, there is easier chance for electron transfer. They show not only plus 3, plus 3 is a common one where it can be oxidation states can be plus 3, plus 4, plus 5, plus 6, and even plus 7. The highest oxidation state in by shown by actinoids is by is plus 7 by neptunium and plutonium. Neptunium and plutonium. Any general, now coming to general characteristics of actinoids. All actinides are radioactive. They are silvery metals. They are highly reactive. In finely divided state. They are paramagnetic in nature. Actinides are slightly affected by concentrated nitric acid owing to the formation of protective oxide layers but highly affected by hydrochloric acid. They form oxocation in higher oxidation state like NPO plus, etc. Let's see the properties again. All actinides are radioactive. It's important to remember this. They are silvery metals. They are highly reactive in finely divided state. They are all paramagnetic in nature. They are affected by nitric acid to forming of protective oxide layer and highly affected by HCl. Then they form oxocation in higher oxidation states. They are not very high. Here it is plus 3 and here it is plus 4 or plus 5. All actinoids are radioactive. They are silvery metals. They are highly reactive in finely divided state. They are paramagnetic in nature. They are slightly affected by nitric acid, forming protective acid, but highly affected by hydrochloric acid. They form oxocation in higher oxidation state like neptunium oxide or uranium oxide. That is the general characteristics. Okay. Point 5f electrons are more effectively shielded from nuclear charge than 4f electrons. This is a point. Why? Because 5f electrons are outside and are less firmly held. And available for bonding. Then one more point is actinoid contraction is greater from element to element compared to lanthanoid contraction. Because 5f orbitals are poor in shielding than 4f electrons. Orbitals, sorry. Then the reasons why it is hard to study actinides. The reasons it is difficult to study actinoids is because actinoids are radioactive, very dangerous, radioactive. So if the person who is studying them is not very careful, they might get cancer and other health issues. So the study of actinides should be done in very high protection and safety regulations. They are radioactive. Half life of them is very short, from 3 minutes to 24 hours, meaning like the the substance will get degenerated or hard to study. It will undergo decay in just very less time. They can only be prepared in nanograms. There are a few more topics. Let's just finish them. The differences between lanthanoids and actinoids. Electrons enter into 4f orbitals for lanthanoids. Electrons enter into 5f orbitals for actinoids. Lanthanoids, they are radioactive except uh, promethium. It's a point remembered. Only promethium is radioactive in lanthanoid. All are radioactive in actinoids. Binding energy of 4f electrons are higher in lanthanoids. Lanthanoids are less basic. We saw this as a character. Basicity will decrease from left to right. Basicity decreases from lanthanum to lutetium. Covalent character of cation increases. Let's write a table and write lanthanoids. That was a very straight line. Okay, it's not. Okay, now it's very straight. Actinoids. Binding energies of 4f electrons are higher and hence can only show lower oxidation states. Binding energies five f electrons are lower and hence show higher oxidation state. Less basic. They are more basic. Maximum oxidation state in cerium max oxidation state up to +7. Neptunium and plutonium. 4f electrons greater shielding effect, 5f electron poorer shielding effect. Then lanthanide contraction is lesser, actinide contraction is more. Then there is one final topic, applications of D and F block elements. Applications of D and F block elements. Iron and steel used as construction materials. Many of the buildings, many of the factories, all of them are at a certain point use these two ingredients. Some oxides of D block like titanium oxide used in pigment industry, MnO2 used in dry cell, that is like Lanche cell, and zinc, nickel, cadmium used in batteries. This we'll see in electrochemistry. Then titanium chloride with CH3 thrice aluminium. This is known as Ziegler Nata catalyst. Used in manufacture of polythene. AGBr, silver bromide. Before it was used in photographic films, has special light photosensitive properties. It was used in photography. Used in used as catalysts. D block elements used as catalyst in many industries. PDCl2, Waker process, catalyst in oxidation of ethine to ethanol. Then nickel used in polymerization of alkynes and other organic compounds. Polymerization, hydrogenation, etc. Like benzene, Then UK copper coins are copper coated steel. These are the applications of D and F block elements. Let's read them again. Iron and steel are used as construction materials. Some oxides of D and D block, like titanium oxide used in pigment industry. Titanium oxide used in pigment industry. MnO2, zinc, nickel, cadmium used in batteries. Titanium chloride with CH3 thrice Al is a Ziegler-Natta catalyst used in manufacture of polythene. Silver bromide used in photography as it has light sensitive properties, used as catalyst in many industries. PDCl2 used in Waker process, oxidation of ethine to ethanol. Nickel used in polymerization of alkynes and other organic compounds like benzene, mainly used in hydrogenation. Nickel and its complexes. Nickel complexes used in polymerization of alkynes and other organic compounds like benzene. UK copper coins are copper coated steel. Let's see one more time. Iron and steel, easy to remember, construction material. Some oxides of D block, like titanium oxide, used in pigment industry. Titanium oxide is pigment industry. MnO2 used in dry cell. MnO2, zinc, nickel, cadmium used in batteries. Titanium chloride with CH3 thrice Al is used as Ziegler-Natta catalyst in manufacture of polythene bags, etc. Silver bromide has special light sensitive properties, used in photography, used in catalyst in many industries. Palladium chloride used in Waker process as oxidation of ethene to ethanol. Nickel used in polymerization of alkenes and other organic compounds like benzene. UK copper coins are copper coated steel. That's with the D and F block chapter. D and F block chapter is done with here. I thought of making a single video of all the chapters, but it seems the D and F block chapter itself took so much time. So I will cut the video into parts.